So we talked about the acceleration idea last time. We talked about a couple of things. One of them was acceleration. So what was the acceleration idea? We have complicated optimization tasks in hand when we are doing any kind of machine learning or data science. And one problem that you could encounter is like your optimization could get stuck on a local minima where you don't hit the global minima. So the a kind of old idea is called momentum. You just push it in the direction of the latest update a little bit on top of doing a gradient correction. That's sometimes it's called Pollak's heavy ball method, but I think you would usually see just momentum. So if you open your whatever library you're using, pick, we talked about some algorithms last time, eta grad, eta delta, blah, 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 right? And all of them, there will be an added hyperparameter called momentum. And that hyperparameter is literally how much you're pushing in the direction of the latest update, okay? Okay, however, we discussed this momentum doesn't always work. There was this particular example where it keeps zigzagging. And it is, well cooked so that it doesn't even do cycling. So in that example, there is no convergence with this momentum method because apparently it literally gets into a cycle. So this kind of stuff can and do happen. So we will talk about how you could deal with this kind of things in practice. There is no fixed recipe as you could imagine, but there are some things we learned trying to look at these algorithms and analyze them. So somebody who worked on it with a little bit more rigor is Nesterov. And his idea was, instead of first doing the gradient and then pushing in the momentum direction, let's first take the momentum direction and then do the gradient afterwards. You got that and then gradient. Here, instead, you're doing the gradient and also momentum. I think this is your momentum in this case. This is your gradient combined. This is where you get. All right. So Nesterov was able to do a lot of rigorous analysis of his suggestion. And in particular, he managed to prove the following. So if you only look at convex, L-smooth, nice function collection, and look at, you give me an algorithm, and I picked a nasty option among those nice functions. Okay, you give me an algorithm, you say, this is my optimizer. And I have the right, this is like a game, and then I'm able to go pick a function which is convex and L-smooth and nice, but still your algorithm takes a lot of steps to run. So out of this game setup, what's the best we could do? What is the limit of efficiency? So he ends up proving there is nothing you could do better than 1 over number of steps squared convergence rate, basically. So if you took t steps, and if your error is decreased by starting error divided by t squared, in this worst case game setup, this is the best you could hope for. There's a lot of math to prove this, but his reason of doing all that math is it's going to justify his suggestion. He proves this particular method achieves that 1 over t squared rate for whatever function that is convex and L-smooth you throw at it. So in a very narrow technical sense, he manages to prove his idea is the optimal thing you could do. And sometimes people call it Nesterov's optimal algorithm because of that reason. Funny enough, though, in libraries, usually this would not be ready implemented when you're using this eta grad, eta delta, blah, 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 because they are already messing a lot with which direction we should go, what should be the learning rate. People think combining that with Nesterov would probably be too complicated. However, if you're running just stochastic gradient descent, suppose you open your PyTorch, look at your STD library, stochastic gradient descent, there you would see Nesterov implemented. Usually, most standard packages don't put Nesterov inside more sophisticated algorithms we talked about. But if you're just using stochastic gradient descent, usually there will be a Nesterov hyperparameter, usually Boolean, like true or false. And if you turn it on, it starts doing Nesterov's method. Yeah. Okay. Let's see. And then okay, this doesn't always work, like seems to do well in convex and L-smooth. And as I said, he did all this math to justify. And like, let me show you another nice illustration from this Andre Vivicino's blog post. This is again the same thing with a particular step size. Just to iterate, yk is first I'm going in the direction of momentum, then doing the gradient descent. Okay. That's Nesterov stuff. And how would you analyze it? Before I talk about how would you analyze it, you might wonder, why do you even care analyzing this kind of stuff? Okay. So this is about like what kind of user you want to be in terms of algorithms. We usually learn how to do better algorithms when we try to analyze what we came up with already. But there should be some kind of like dialogue between trying to design algorithms, experimenting with them, and the ways we analyze them. Okay. So our way of teaching this is not fully modern, unfortunately. So a lot of CS majors in the room, probably you guys took some algorithms class, right? And then you probably learned about depth first, breadth first, all kinds of nice, good graph algorithms. And in the algorithms course in standard, graduate, and undergraduate, we only teach looking at algorithms from a worst case perspective. What does that mean? I am going to run a particular algorithm on a graph with n nodes, and for the nastiest graph ever, how long it will take. This is our measuring stick, comparing algorithms with each other. If you took algorithms course, that's what you would usually see. However, that does not necessarily reflect when you're actually using that algorithm on whatever application you're working on, right? So there is a lot of development within computer science trying to analyze algorithms on some data models instead of like the worst case. Come up first with some probabilistic statistical model of what you're seeing in your application, then analyze your algorithm on that model and see in expectation for that randomness, the number of steps you get, how does it look? A simple example would be, say, think about like sorting algorithms. You got numbers, you want to sort them from small to big, right? And then if you look at in the worst case, the algorithms you get that seems to be fast in worst case does not necessarily going to be the ones that are going to be fast in practice, okay? And this is the simplest algorithm you could think of. You got numbers, you're going to sort. If your way of analyzing is failing there is something wrong with it. So, but if you look at it from a more data-driven perspective, for example, if you're running a call center and the number of calls come in very random time intervals, it's almost like uniformly random from the beginning of hour to the end of the hours, right? And you're going to sort it out, send it to customers. Servicing people used to be probably AI agents very soon, right? So, and in that case, there is this thing called the radix algorithm or bucket sort. You can prove mathematically in this type of data, it is the fastest and it actually behaves fast, right? Things like that. So, and why am I saying all this? This is all teaching us how to do better algorithms, and the good algorithms that people manage to design somehow, sometimes intuitively. That happens. Somebody comes with some intuitive great idea. It seems to work. Then it also changes the ways we analyze algorithms. So it's back and forth. Okay. So when people try to analyze this accelerated gradient descent, they use this function. They use this idea coming from mostly dynamical systems people. But in computer science, we call it potential function. Dynamical systems people or engineers sometimes call it Lyapunov function. The name doesn't matter. The point is like, you're going to get a function as you iterate your algorithm, that function is going to decrease. It's like a potential decreasing. And when it hits the lowest possible, that's the time to terminate. And using the decrease in the function, you estimate the number of steps it will take. That's the general idea. And then let's say you try to run this on a very simple function. Let's say it's like quadratic, like this, like a nice function that I'm trying to optimize. X times a matrix times another X, and then some vector times that X and some number, some nice looking function. Try to analyze this Nesterov or accelerated gradient descent on this and see, well, what do I get out of it? Maybe let's analyze, say, momentum on this and see what's a good momentum parameter to pull in there, get an idea. And then they go into it, and then, you look at the gradient, it comes out this way. And then, gradient 0 is like a local optimum condition. This looks like it's telling me the optimum should be something like Q inverse times B, You start doing math, and then you write down that parameters. So it's like the momentum kind of I'm pushing. It's like the learning rate. And I want to pick the best alpha and beta so that I get wherever I want to go quickest, right? And so one way you could do this is like you write these equations using a matrix. I did not write the explicit matrix, but you literally encode these like momentum first and gradient descent idea using a matrix that looks recursive. Xk minus 1 minus your optimal, xk minus your optimal, times some matrix gives the next one. And that matrix literally encodes this alpha, beta, whatever parameters you picked, right? And then the reason of writing it with the matrix is like then it becomes kind of easier to keep track. At every step, I'm literally multiplying my vector with that particular matrix. And I'm keeping using the exact same matrix, more or less. And then using this way, and why am I always multiplying with the exact same matrix? Because my gradient here is very simple. It's just there is a matrix multiplied with your x, okay? This is not true for every function. I'm working on a specific function. And the reason working on the specific function is, let me analyze on the simple case to get an intuition on what should I expect for other complicated functions. And then you look at this and you think about like, if this guy is say magnifying this vector tiny bit, it say takes this vector, multiplies it by 2. Well, while you keep iterating, it's going to get magnified and magnified. You don't expect to get to 0 and stop, right? So to expect any like convergence, this matrix should be somehow shrinking what's going on. And the error should get smaller and smaller. And then at some point it will be 0. And when you see error 0 here, you're at the optimum. And how big that matrix like magnifies stuff, as we talked about, is controlled by this eigenvalues, singular values. So that's the definition of them. So you just really look at this T matrices eigenvalues and look at the biggest one among them in terms of absolute value. And if that is small, this guy is shrinking. So this you don't need to know, but the name for it, if you see, it's called spectral radius. Look at all the eigenvalues. Look at the biggest one. And if you know that is already small, a little less than 1 is good enough, As you keep iterating something less than 1, it's going to get smaller and smaller. And okay, that's what they end up proving. There's some math here, don't worry about it. And basically, what they end up proving is this. The error is less than equal to that spectral radius raised to the power number of steps. Suppose if this was half, if you go like 100 steps, you're already dividing by 2 to the 100, which is a huge number. Okay. So if your spectral radius is somewhat small, you're in a good shape. And then there's something that's going to come out. This should have been Q. I'll fix this. Also related to your function, Of course, you also expect this Q in your function to come into the game. And it comes through the biggest and smallest singular values of that matrix. And again, that is not strictly important, but that's what we get out of this analysis. It is related to this, like how much shrinking is happening at every step of the iteration. And then the matrix that I am trying to optimize over, this comes from my objective function. It was like X transpose this matrix X plus some linear, some number. How well conditioned is it numerically? This is a measure of like the biggest singular value divided by singular value. If this is 1, your matrix is like perfectly conditioned. It's like behaving to every vector the same way. This is how much at most it's stretching. This is how much at least it's squeezing. If it is like treating everybody the same, then it's going to be, we would call it perfectly conditioned. If your matrix is, say, 5 times the identity, like it will treat everybody the same. But if your matrix is not far from that, still good. And this is how the analysis comes about. And then people work harder on it. They say, okay, we are able to do all this math, so let me actually go try to optimize the best alpha and beta in that momentum. I did all this math. Maybe I could push it more, and I know literally like the best choices, for this at least simple function. And I figured it out. I think if I took note correctly, it comes out like this. Apparently, you go look at that matrix Q. If this is the biggest singular value, this is the smallest. The optimal comes out as complicated looking stuff. Okay, so, but the point is like you can literally go find the optimal step sizes. And then now we did this optimal picking for like a nice cherry picked function. And we are going to hopefully derive some intuition from it, or like in the wild what I should do. So what you noted is like if you would know everything about that matrix, biggest singular value, smallest singular value, you would know the optimal stuff. And I expect in the wild my matrix to be kind of wild. Okay, what does it mean? I would expect this guy to be much bigger than that. So my matrix may be squeezing some vectors, like dividing them by 1,000,000 and stretching some other by 1,000,000. In that case, this means this is going to be like 1,000,000. This is going to be 1/1,000,000, right? In that case, you see this looks like almost 1. This is small compared to this. And this plus that doesn't change so much. So it's going to be pretty close to 1 in that case. And then this is going to be some complicated looking thing that I need to know what this is to have any idea. Okay. So what people do in practice is like you would go pick a big momentum, 0.9, 0.999, not too far from 1. And then they would usually do empirical cross-validation, a whole bunch of experiments to pick the best alpha. You kind of fix your momentum to be high, and then you try over different alphas and see which one works best. Or you could also try different decay strategies for your learning rate. You could say linear decay, exponential decay, The rest is usually a lot experimental. The intuition that from analysis and also from a lot of empirical experience suggests, putting momentum high, close to 1 seems to be a decent idea. But there's like a cutting edge type situation. So not cutting edge, like bleed, like how can I say? Like edge of a knife. So let me try to show you what I mean. And the optimal happens close to edge of a knife. That's the issue. Try to ignore the news popping up. Yeah. So I put this link. I showed this to you last time too. So let's say, the momentum is already picked out high. Let's say give it some more juice. Yeah. Or let's say I fixed the momentum high. I'm trying to optimize over alpha. You see, there's like a kind of edge of a knife in the sense that the optimal behavior versus like things starting to go crazy, there's some transition which is hard to predict. Okay. So this is also kind of the intuition people seem to have. The best learning rate is not too far from things going crazy sometimes. So in experimentation, you got to be a little careful to figure out when you're at that edge, okay, maybe that's the sweet spot. It's not too bad to be on the cliff, basically, for this type of stuff. But this is all, this is not very scientific, but this is the best we could do so far as I know. Okay. Okay, that's momentum stuff. And we will do a little bit more on this today. Let me get back to my presentation. And what is that a little bit more? It's called Adam algorithm. This is the algorithm I'll walk you through, don't worry. So what is the idea in Adam? The idea is like we learned this momentum giving us some advantage. And we also have seen these other algorithms like Ada Delta, Ada Grad, RMS Prop. They were trying to pick the learning rate and a matrix looking like a Hessian, but cheaper to compute to get a good direction. And the idea in this Adam paper is like, can we try to combine all these wisdoms and mix them up and use all of them to get a fast algorithm? Okay. And let me walk you through how that goes. As you see there, so there is going to be two parameters that they will pick. So first, just like the algorithms we have seen, they are creating an accumulated average of the gradient vector. This GT is that gradient vector at step T. This is the previous average. And you're taking beta 1 times this, 1 minus beta 1 times your latest update. So depending on your beta 1, the averaging will change. Right? So beta 1 equals to 1 means you forget about the last step. 0 means you only remember the last step. And in between, it will be like averaging over. And how like drastically you average is up to you to pick. That's like this averaging window idea that we have seen in Ada Delta. And then the second idea is like, let's also try to accumulate an estimate, like a moving average of gradient times gradient transpose. So this was the way that Ada Delta and Ada Grad was trying to estimate the Hessian, if you remember. You take gradient times its transpose, and that's a matrix, and you try to keep a moving average of that quantity. And you expect this to be a reasonable estimate for Hessian, then you will use inverse of this matrix like Newton, something like that. Okay, that's the second thing. And again, you could change the way you average over, how much aggressive or moderate you will be. The main update in this algorithm versus the things we have seen before, this person sits down and does some probability estimates in the following sense. He says, if I'm trying to run like this stuff with stochastic gradient descent, even my function could also be somewhat stochastic. And I compute expectations and whatnot, how much bias this process would be pushing into. I pick this beta 1, I pick this beta 2, I'm sampling some stuff, doing my gradient, keeping running this iteration. Like how much far off I am from the actual estimate I would like to make. And he computes those probabilities and he realizes this is like on expectation, the bias added by this process, and he corrects it by dividing with that. So at the end, in expectation, you don't have any bias. Okay. So that's the main innovation of this algorithm. It just adds a little bit of probabilistic reasoning on top of what was already there. And, not so lucky for the person who invented Ada Delta, this kind of took over. So now people are usually using Adam without even thinking. Like it kind of became the default algorithm. I don't know how that happened. But it doesn't have to be. But they're all, as you see, they're all kind of similar to each other. But I think it's a nice paper, so no shame on using this all the time either. And as you see, even in the algorithm description, they wrote the parameters they find in their experiments. And they find this momentum-like stuff or the moving average stuff close to 1. And for learning rate, this is being a little conservative. They fix it to a small learning rate all over the place. Probably that was their way of guaranteeing some convergence. If you pick your learning rate big, it can keep going back and forth when you have to converge. But this doesn't have to be. So this alpha, you could play with it as you like. Okay. So that's the Adam algorithm that is trying to combine somehow the intuition that came from the earlier algorithms and the fact that we learned momentum is helping us. And that's kind of about it for this stuff. Now I'll switch over to something else if there are no questions. Let me wait. So what did we do so far? We talked about what's a descent algorithm, gradient descent, stochastic gradient descent, different versions of it. And we talked about kind of what's called preconditioning gradient descent, in the sense that you take that gradient vector multiplied with a matrix or something to make it look nicer. And the versions we talked about was Ada grad, Ada delta, and RMS prep. And after that, we discussed acceleration and momentum. And today I recapped that and also gave you an algorithm that tries to combine all these ideas together. Of course, this is not the end of the story. People will keep inventing different versions of optimizers and them working for different problems better, probably. But one thing that is so far not addressed is everything we are doing is assuming I could compute those gradients. And not every function is differentiable. Just think about L1 norm. It's very natural, it's not differentiable because it involves absolute values. When you have an absolute, it's like this, right? So we need to address that. So what I do if I don't have differentiability all the time, we'll start talking about it either today or in the next lecture. That's one thing. Second, everything we have seen so far was like unconstrained. We did not put any limitation on what kind of parameters you could play with. We're just optimizing over, trying to pick the best one. But in reality, usually you have some constraints on your parameters. If you're actually modeling something, this parameter should be between such and such sometimes. If you're using a gigantic deep neural net, probably you have no idea what parameters is correctly. But in certain cases, you have constraints on your parameters. You may want them to be always positive, for example. That makes sense. And this is not addressed either. So far, the biggest limitations of our discussion, assuming differentiability and always being unconstrained optimization. Okay? And that's what we will start addressing now. Let me pause. Let me stop this.